Okay, hi everybody, and welcome to the Overplanetary Virtual Lunch. This should be the number 46, if I'm not wrong. So this evening, afternoon, depending where are you from, we'll have Uda, and she will talk us about the machine learning activities in the Europlanet research infrastructure. And I mean, me and Uda, we know each other because she's managing this activity. I'm one of the small part of the activity. So Uda will you please talk a little bit about all this machine learning activity that you are managing?
Okay, yeah, thank you, Mario. And thank you also for the opportunity to present here our machine learning work package. And also good morning, good afternoon, good evening to everyone here. As Mario said, I'm the work package lead of a machine learning work package within the Europlanet 2024 research infrastructure project. This is a EU Horizon 2020 research project. My name is Amerstorfer. I work at the Space Research Institute of the Austrian Academy of Sciences in Graz in Austria. My scientific background is more plasma simulations, specifically magnetohydrodynamic simulations of boundary layer instabilities, and also the evolution of atmospheres of terrestrial planets. And more recently, I was also working a bit on doing some research on space weather and coronal mass ejections. So I come more from the scientific side. Just a few words about Europlanet itself. This is a project, Europlanet, and the services that Europlanet provides that already exist for over 10 years. The latest research project, which is called Europlanet 2024 Research Infrastructure, started last year, the beginning of last year, right before the Corona pandemic started. Europlanet 2024 is led by the University of Kent from the United Kingdoms. We have 57 beneficiary institutions and the further 44 affiliated partners from around 25 countries in Europe and all around the world. And so Europlanet provides different services. For example, the most important are it provides transnational access to some laboratories and field sites across Europe, and also new now we have also some facilities in South Korea and China. It provides virtual access to different services and tools. Probably some of you know, for example, Vespa. And it also provides networking activities to generally support the planetary science community and also planetary missions. Many of these services, as I said, already exist a couple of years, and machine learning, however, is one of the new branches that Europlanet includes now. And so machine learning, our work package, cannot build on a legacy of previous services. So what is now the aim, or what are the aims and the objectives of our machine learning work package in Europlanet? So we want to develop and provide data analysis tools that are optimized for planetary science. So machine learning, of course, is a technology, or let's say within machine learning technologies have been developed over like the last couple of years. It's quite well known in big data industry applications, and it's becoming more and more popular also for science. And so we want to integrate this machine learning expert knowledge that's there from the industry side also into the planetary science community. All the products that we produce, all the codes, trained models are open access and are freely available, so that everybody who wants to use them, wants to modify our products can do that. So with this, we want to demonstrate the capabilities of machine learning, and we want to foster the use of machine learning in, let's say, data-driven space and planetary research. And with all of this, we want to generate a broader discussion on using machine learning in our field or in different fields of science. As Mario said, he is one of our work package beneficiaries, or the DLR is one of the beneficiaries, and we have I show here the list of all of the beneficiaries. We have quite a nice mix of private companies, as Acri ST, also know, in Austria, who, as I said previously, also who bring in their expertise in data analysis and in big data analysis and in machine learning. And then on the other side, we have like the institutions that come from the science side. During the proposal phase of Europlanet and also of our work package, we ask different institutions to submit science cases or use cases where they think that machine learning can support their research. And at the end, we have now somehow 8 or 9 science cases that we work on in our work package. From the science cases are from different fields of planetary science. For example, as we can see here, there are science cases dealing with the detection of plasma boundary crossings around planetary magnetospheres or in the solar wind, or also the detection of coronal mass ejections in situ solar wind data, which is closely connected to the analysis and prediction of space weather events. So those deal specifically with time series data and also use supervised learning methods. But also there are science cases about surfaces of planets. For example, here one science case deals with the classification of surface composition of on the surface of Mercury. Also mineral identification in reflectance spectra, or planetary features on Mars and their automatic detection. So as you can see, there are science cases where you have time series data, or where you have images or spectral data. So we hope that at the end of our work package or of Europlanet 2024, that we have like a nice handsome, let's say, machine learning tool set, which is as specific as needed for the individual science cases, but as general as possible, so that that the scientific community or that other researchers can use those tools or codes or trained models for their own research with, let's say, small modifications to the machine learning code. We have So far, we have worked on 4 science cases in more detail, and those science cases were also presented at different conferences, or the preliminary results were presented at different conferences. And I just want to show some slides of those presentations from this year's EGU about the preliminary results of some of the science cases. So this is the work that that our beneficiaries did. So here, for example, at this year's EGU, the Alexandra from the Moscow State University presented the automatic detection of magnetopause and Bowshot crossings in messenger data, a convolutional neural network there was trained on 5 classes to detect in the magnetic field data the different crossings of the boundaries around the Mercury magnetosphere. So for this, the orbits were labeled manually, and then, as I said, a CNN was trained on the first 50 orbits. So here on this plot, you just see on the top right plot, you see the magnetic field magnitude, and you can the black lines show just the inbound and outbound boundaries of the Bowshot and the magnetopause, and then again of the magnetopause and then Bowshot. And the lower plot shows the magnetic field components. So as I said, the CNN was then trained on the first 50 labeled orbits, and here is the preliminary result, the confusion matrix for this classification on these 4 classes. So the classes are the interplanetary magnetic field, the IMF, then the Bowshot crossing, PS crossing, magnetopause crossing, MP crossing, the magnetosheath, and the magnetosphere. The performance on the first look looks quite nice, but there is one problem, that the classes are rather imbalanced. So you have, most of the time, of course, you do not have one of the crossings. So the classification performance is biased in that way. And next steps in this science case, for example, include to include more orbits. So then we have more data, and hence we have more variation, which might improve the results and reduce the bias, let's say. Or also we want to include other or use other techniques. For example, we want to add additional features or Fourier transform. So yeah, but the first preliminary results look quite promising, and I think we are in a good way. Another science case that has been worked on in the last couple of months from one master student at the NO Center in Graz is the detection and classification of interplanetary coronal mass ejections in solar wind data. This is somewhat similar to the boundary crossing science case, let's say, because here we also have solar wind data or time series data, and we want to detect and classify one event. In the Mercury boundary case, it was the Bowshot and magnetopause crossings. Now it's the start and the end of this interplanetary coronal mass ejection. So here again, here in this case, we have to say that there was one already publication doing something similar, which was published in 2019. And so the master student at the NO Center re-implemented the pipeline that was proposed there. And in the 2019 paper, they applied their pipeline to wind data, and we additionally included stereo A and stereo B data to have multiple spacecraft data. And so we were able to reproduce the results when we applied our model to the wind data, but interestingly, when we included additional data from stereo A and stereo B, then the precision of the results went down considerably. So it seems that these three data sets are very different from each other. And we have to try to, let's say, try to figure out why exactly stereo A and stereo B do not perform as well as the wind data set. And also we want to explore better post-processing techniques to improve the performance for this science case. So those were two science cases dealing with time series data. We also have been working on one science case dealing with images. And this one is about the automatic detection of a specific surface feature called mounds on the surface of Mars. Here, the University of Passau did, let's say, most of the work from the machine learning side, and they developed a generative adversarial network to detect those mount features on the surface. As you can see, the slides from this talk at this year's EGU is rather technical, so I will just concentrate on the results, and you can see here on this right image with the image tiles, the predicted mask, and the ground truth that this network performs rather well already. When you compare the predicted mask and the ground truth. Also here, it was a further approach was explored, namely to simulate the terrain with these masks. And so the key result here from this science case is that learning the representations based now on simulated data can definitely improve the detection accuracy. And then also Mario did already nice work on his science case, and probably Mario, could you say a few words about your research?
Yeah, thank you. Yeah, just a few words. So just to give you an overview, what we were aiming at was to use the data from the messenger mission, so the NASA messenger mission that was ended a couple of years ago and was very successful in remote sensing analysis of Mercury, because Mercury was not that well explored at the time. So now still, but was relatively unknown. And one of the problems was that the spectrometer, so the mass spectrometer, was expected to investigate the 1 micron band that was really useful to identify minerals normally. But we were surprised to have, as you can see, this couple spectra here, almost no signature in this area. Those spectra are going from 300 to something like more or less 1,000 nanometers, so towards the 1 micron band. And the problem is not yet solved, why they are so flat. And I mean, there is not a lot of literature on this data, and we thought maybe there is some information buried in this data, and we try to apply different machine learning technique. And one thing that we come up with was doing several kind of data compression and learning about the data structure, then classify those data, and we end up with this map that you see in the upper left side. The color are just different classes, and the classes are ordered with the slope of the average spectra of the classes. And you see that there is a spatial coherence of these classes, even there are no apparent absorption feature in the spectra. So if you compare with the map, the bottom right, this depicting you the northern smoke plain that are a volcanic area concentrated in the north part and even in other part of Mercury, is more or less closely related to the red class that we found there, but it's not exactly the same. And we think that this is related to the due to the coupling, to the rotation, to the spin and the rotational Mercury. There are strange pattern of the equatorial hot region that are those big secret you see in the top right. And we think that these two effects in somehow are linked. So we have different composition, different volcanic region, plus different yearly top temperature that changing the spectral signature of this mineral. All these things together give us these spectral classes that we see there. Yeah, that's more or less, not going to too much detail, I guess it's more or less what they've done.
Okay, thank you. Yeah, so as I said, all these preliminary results and the slides out of those presentations from the EGU yeah, were presented at the EGU. And probably one interesting thing for you now is, so you know that we are doing something in machine learning. You know that we are working on some different science cases or automatic detection and classification things. And I said that all of the tools and codes and models that we produce and we develop are open access and free to use for everybody, but where can you now find them? So we set up a website. You can reach it under this address that's given here on this slide, and we call it Machine Learning Portal. So this website is still under construction, and there will be new content added continuously. For now, there is yeah, some basic information about our machine learning activity within Europlanet. Of course, the details of the science cases, and we will also put up there some basic machine learning tutorials and also tutorials and documentation specific to our science cases. Those are not there yet, but we're working on them. And you can also find announcements of conferences, sessions, workshops that are dealing with machine learning content. So feel free to check that website from time to time if you're interested about our activity. The codes and trained models themselves you can find on our public Github organization. Yeah, basically all of the code is written in Python, and you can find there Jupyter notebooks, for example, or the trained models for the science cases. You can find their documentation on how to, let's say, how to install or what requirements are needed to run the code, and also what you can do with the code and with the models, and probably what more important, what you cannot do. And also you will find the code for the machine learning tutorials that I was talking before. So if you think that that some of the code or models can support your research or your data analysis problems, then feel free to download any of the scripts you can find on our GitHub organization. And if there is an issue, please file an issue. We want to actually involve also the community in our development process of our tools. And then last but not least, of course, we plan to hold workshops about dedicated to the science cases and to the machine learning tools developed for the science cases. We will have 2 workshops still in this year. The first one will be during the EPSC, the European Planetary Science Congress, in September, and the second workshop will be a couple of weeks after that, hopefully still in this year. So we plan it for end of November. Of course, more workshops are to come in the next 2 years. And as I said before, we announced those workshops on our machine learning portal. So if you're interested to participate, I will say that the workshops in this year will be online workshops, of course. And yeah, nobody knows if it will be possible to have in-person workshops in the coming years. So if you're interested to participate in one of these workshops where we will present our science case and the tools, and we will offer support on how to use the code, the trained models, or probably also how to modify the code for your needs. So check out the portal for the announcements for the workshops. Yeah, then that's it from my side. Thanks for your attention. And if you have questions or if you're interested in a closer collaboration, please just drop me an email